give a short presentation of how we can do the studies in a tool like Dixieland Power Factory. And this is a model that I assume that you know. It's the sort of famous 4-machine, 2-area system with 2 generator here and 2 generator here. I have sort of modeled these as a hydropower unit and these as thermal units, but it's not that important. The important is that there is higher load here and there, so that there is a power transfer across this corridor between the 2 areas. And we are interested in the oscillatory modes and the behavior of this system. So to illustrate that in Power Factory, you can choose between different types of analysis. If you want to do simulation, for example, you click simulations, and when you do a simulation, you have to define some disturbances or things to happen, or it will be very boring. So there is ways of defining events. So in this case, I defined a number of events, but the ones I will be running is just a short circuit at bus number 8 at t equals 1 second, and a clearing of this fault at 200 milliseconds later. And this is configured then, so I can initialize. That's the starting guy here, initialization. Execute that. And it updates the parameters. And then you can, it's not so good to see, but you can zoom in, for example. See, I mean, again, I don't know if you see it, but all the variables are here. I mean, how much the voltage on the bus and the angle and the power flow, active and reactive power on the lines are shown here. Zoom in a little more. Now I think you can see. So 221 kV here, angle minus 5.7 with respect to a reference. 200 megawatt is flowing in this line, and 7.8 megavars reactive power. And you see this almost the same here. That's a certain amount of losses. And there is a supply of reactive power from both sides. That's the power flow. Let's run the simulation. Then you type the other guy. I run for 10 seconds. And I can look at active and reactive power. And you can make a lot of different plots, of course. That's up to you. But here you see the short circuit and that there are power oscillation. Generator number 3 and 4 is obviously in phase. But the generator 1 and 2 is somehow out of phase, and it's not clear sort of what is the frequency, their frequency either. So if you want to dig deeper into this, you can look at the modal analysis, but you can also take a look at speed and rotor angles, of course. And here it's a little bit clearer that the speed deviation is highest for generator 3 and 4, and that there is something here on going on between generator 1 and 2. And then to investigate that further, following what we had talked about earlier, we go to modal analysis. Do a restart if necessary. And here it says modal analysis, so we can compute eigenvalues and eigenvectors. We will, since this is a small system, we will compute them all by the QR method. And we can look at the results. Now I'll look at eigenvalues. So I click that. I'm running this remote now from our university, so the dialogue takes some time. The simulation is fast, but updating the screens takes a little more time. And then I would rather sort that on damping ratio. You get all the eigenvalues here. It's 40 of them totally. Okay, the other way around. Now, like yesterday, we get one eigenvalue that is 0. So that's normal. You almost get one 0 eigenvalue. But the other here now, look at this one, mode number 18. It has a frequency of 0.45 hertz and a damping of 2%. That's number 18. And then the other critical one here is number 15, which has 5% damping and the frequency of 0.7 hertz. So let's take a look at these ones. 15 and now 18 and 15. Then I go back here and look at the states, and first look at 18. And then what I get now is a list of all the eigenvectors left and right for this mode, and also the participation factors. So what I can do to interpret it is to sort it on state variable, because referring to no, okay. Yeah. Referring to what we talked about yesterday, when we set up the equations, we get 4 equations for speed, since we have 4 generators. We get 4 equations for the transient internal voltage, which is these 4, I think. And we got 4 equations for each of the damper windings, so 1. So everything is there. What I want to look at, I wish I could have enlarged this, but I want to look at speed, and I want to look at observability. Probably not easy for you to see, but referring to what we did yesterday morning, here we got the list of eigenvector elements for that mode related to speed. And therefore these numbers here with the magnitude and angle, these are the mode shapes. So if you could see this, you would see that the mode shape is particularly high amplitude for generator 3 and 4. And the other is mostly in opposite phase of that, but lower. And if you look at the other one, number 15, that was the other critical one. Again, sort that on speed, sort that on state variable. What you would see here is that the magnitude of the observability factors here is highest for generator 1 and 2, and that the two generators are almost in opposite phase. So actually this is a mode where generator 1 and 2 oscillates against each other, as was indicated in the simulation, but not so easy to see because sometimes it drowns in other results. So this was just to show how the same analysis that we worked on yesterday can be done with these tools. Okay. Okay, so the last item on agenda for this week, from my side in a way, is what I've called dynamic interactions and control in hybrid AC/DC systems, which are becoming increasingly sort of interesting in many places. The outline, introduction to the area about interconnection of AC grid with DC. And then we're talking about, from my point of view, it is that this is mostly related to offshore grids, but it may not be. It could be also in a country like India. You could think, which is a large country, you could think that you have an overlaying DC grid which interconnects the system instead of having one AC grid. I think that is actually a good solution for many reasons, that one should think of having a DC supergrid in a way and more smaller AC grids. Then the question becomes, how do you control such a system? How do you exchange reserves like you would in an AC grid? How does it behave in terms of dynamics? Is there any dangerous adverse interactions when you interconnect AC grids through a DC? That is research activities that we have been performed in several projects. First of all, in a research center for offshore wind technology, where this is particularly relevant. Also in other European and Nordic projects. It's also activities on this related to our laboratory, and there has been national PhD project. So, what is the motivation here? As you know, or may know, there is high activity on wind power very much in Germany, in Denmark, and in the UK. And they are looking offshore. There are coming up quite a number of offshore wind farms in Germany and in the UK sector of the North Sea. While seen from a Norwegian perspective, we have interest in supplying some offshore platforms for oil and gas exploration through DC connections. There is a number of DC connections between the onshore and the oil platforms. So why should these be just connected to shore? Why can't you interconnect them in a grid? And there would be several motivations for that. That is relating to not only the grid capacity, but also the ability to integrate the power market, to have more flexibility, to trade the wind power and other across the European system. But when you do that, you need to look at how do you control among the challenges. There are many challenges, of course, but one of the main challenges is control and protection of these grid. So there are a number of challenges. First of all, there is a regulatory challenge. How do we make the different countries agree on developing such a grid? There are country-specific incentive schemes for subsidizing renewable energy, for example. You don't, the English don't want to give away power to Germany and vice versa, so there is issues. How do you design the market to integrate this? But in operation, we talk about stability and control, power system security, and among all, lack of inertia. And very interesting, I think, is the availability and possibility of sharing reserves between the different systems. So that is my focus. And then we start looking at the basics with respect to control of a multi-terminal HVDC grid. You know that when you deal with the power balance in an AC grid, that is very much about adjusting the speed droop of the turbine governors to provide a balance. The same thing, that is because frequency is sort of a global measure of the balance. You don't have much frequency in a DC grid, but you have a DC voltage. Now the DC voltage may not be exactly the same at all the converter terminals, but still it varies very much in the same way. So you can make a control scheme so that you control the voltage as a function of the active power in and out of the DC grid. So if all the converters are equipped with such a voltage droop scheme, they will add up to a total aggregate scheme where the operating point would be around here. And when there is a deviation, the voltage will be adjusted to maintain that balance. In this way, there is no need for communication between the terminals. You make all the converters that are equipped with voltage droop, you make them contribute to the DC voltage regulation. So in contrast to the traditional, the more traditional way of looking at DC, which is that one converter controls voltage and one controls power, so that you have the operating point there. That is sensitive to the one that controls voltage, right? If that falls out, the entire grid collapses. In this way, you can lose one converter and still be operating. So this is more sort of N-1 friendly. So how do you do that? Well, you do it in the same way as basically as for a turbine. The modern voltage source converters, and we are talking in practice, we are talking about voltage source converters here. You cannot make a DC grid flexible and practical with thyristor converters. So we're talking about voltage source, and as far as I know, almost all the new HVDC links that are being built, at least in Europe, are voltage source nowadays. So with that, you can control power with the vector control, and the outer control loop can be just this, have this voltage droop as an additional input. So it's controlling the power reference, but adjusted with the voltage deviation through the droop constant. That's what needs to be done. And then you can have many, this open up for many possibilities, among other exchange of reserve across the various AC networks. What you need to do then, because the reserves are, the primary reserves are activated from frequency deviations in the AC grid, right? You have the primary controllers which increases the power production when the frequency drops, and vice versa. So if you want the DC terminals to contribute to that, they have to sense the frequency on the AC side. And that they can do locally by sensing the frequency on the AC grid and add that to the control. So if you add also a frequency droop setting, that will modulate or influence the actual set point of power. So it's a simple addition to the control based on the frequency deviation in that local grid. So how can that help us in exchanging reserves? That is an example from a PhD thesis that one of my students did a couple of years ago now. we have sort of modeled very simply something that resembles the North Sea area. You can think that you have UK here, England and Scotland maybe, as two nodes. You have Germany, for example, here as one node, and Norway up here. And you have some connection to an oil platform, which is a major load. And perhaps some wind power feeding in. But that's less interesting. And you have this controller that controls the converters based on frequency deviation and DC voltage deviation. The exact configuration of the example here is like this. You have power feeding in from the English side, from the Norwegian side, and you are supplying considerable offshore loads, and you are supplying in Germany in this case then. I think 3 of these terminals are equipped with droop, at least this one and this one as far as I remember. And we'll see that. So what happens then when you have a loss of generation and a sudden need for more power? In this case, there is a sudden need for more power here because you can think, for example, there is a loss of a generator of 200 megawatts. So this needs more power. What happens then? Of course, what happens first is that the frequency drops in that grid. So the local frequency will drop due to the loss of generation. So what happens? The converter at that node responds due to the frequency droop. So the frequency droop senses the local frequency and demands more power from the DC grid. Here it is positive out into the DC grid, so that means 900 megawatt into the AC grid, which increases to 950 approximately. Okay, so you take more power out of the DC grid. What happens then? Then, naturally, the voltage drops. You're loading the grid, so the voltage drops on all terminals. And what happens when the voltage drops? The primary control of the terminal that are in voltage droop control. Now we talk about voltage droop control because a response to this change in voltage is that the power increases. On terminal 1, 2, and 4. And okay, what happens then? You draw more power out of the other AC grids. Well, then it's like an additional load. So then the frequency in those grids will also drop. So in this case, we have transferred some of the problem from one AC system to all the others that are equipped with droop control. So they help each other, even though they're not synchronously connected. That is the simple way to explain how this works. And why do we want to do that? Well, it's simply because we want the system to act like an interconnected grid that support each other. So without this support, you might say that you could have a severe voltage frequency drop, but with the support, the voltage drop is very much limited. I mean frequency drop, because of the help it gets from the other systems. And then, well, this is good, isn't it? Everything is fine. It's just that we don't know if this will work properly until we do some detailed analysis. So one of my students has who just finished has studied the dynamic interactions if you design such a system. And the main objective is to see if there are some interaction or dynamic couplings that could be significant, or especially could they possibly have any negative effects on stability that we don't obviously see. And the main focus in this study was to look at the interaction between the AC grid and between the AC grid and the DC grid, and look at what factors were influencing the level of interaction. So this is more an advanced study, but also in this case we apply the techniques that we have been talking about these days: modal analysis and time domain simulations. Again, we have a system that is fairly similar to the one I showed before, but now the purpose is to analyze interaction between the AC system, so we need to model AC grids in some more detail, so we can say that we have a system and not only a passive network behind the converter terminals. So on this side we have you can recognize something similar to the 4-generator 2-area system, and a slightly simpler system here with 2 generators. So you would expect that there are at least 1 or 2 modes of interest here, and maybe 3 modes of interest in this one. And what we are interested in analyzing is the interaction between the electromechanical modes in this area with the other areas. Here we talk about inter-area modes between area 1 and 2, right? Is there an inter-grid mode, for example? We are interested in knowing that. So how can we start this analysis? Well, first you could analyze the system when it's decoupled. You could disconnect the DC grid totally and analyze this by itself. Then we'll find, well, very much what you have seen before here. There is a mode at around 0.5 Hertz, which is the inter-area mode between here. And on this side, there is typically some other modes. This one is at 1 Hertz, this one is at 0.9 Hertz, and they're sort of reasonably damped. These are the most critical ones. Then we can connect the system through the DC grid and look at what has happened. The modes are depicted here. This one indicates the 0.555 Hertz. This is in separated operation, and the cross is in connected operation. And the other mode in the area that was seen in area 2 or 3, in area C is called here then, in isolated and connected. Isolated and connected. So you see, when you couple these grids, the same modes are still present, and they haven't moved very much, but they have moved a little bit. And so there is some interaction. May not be very much significant, but there is some. So we can look a little bit. And there are other modes that also move, but are less significant for the stability of the system. Some of the low frequency modes seems to have improved actually, and that may be due to the coupling of the sharing of frequency responses. But this one is has lower damping when it's connected, even though not that much. But still, this is a kind of concern. And we can look at mode shapes. And what we see, if we look at the inter-area mode, this one, is that this is observable mainly in grid A as expected, but it has some observability in the other grids, even though it's low. So there is a coupling, but it's not very strong. This is the coupling. And there's the same with the other grids, but we see the coupling of the other modes is very, very small. And that is, I think, due to the fact that these are much better damped as well. If you do the small signal analysis and do time series simulation, try to do a small disturbance and look at the results, we are able to see the couplings. If we excite the inter-area mode, we can see that mode in the other system. So if you have a short circuit here, we can actually recognize the mode in this side. But the amplitude is negligible. However, when we do a larger disturbance, what we will mainly see when we excite the system is, of course, that this low damp mode is highly visible in the area where you had the fault, but it's not really visible in the other area. But what you get is that excites the dominant mode in that area. So the interaction for larger disturbances is more that you excite the natural mode in that area, not the same mode. And the main point here is that the interaction depends mainly on the control system. So the faster and tighter control you have, the less interaction you have. But if you want to exchange reserves that you and you want to apply DC voltage control, then you also have the interactions. But of course, that is a result of the fact that you actually want interactions. You want to interact. An example of that is here. The interaction of the inter-area mode in grid number A is seen in grid number C, but if terminal B is a slack mode, then there's no interaction with grid number C. On the other hand, it's when terminal B is a slack bus, it is of course an interaction due to that fact. The other way around, the mode in grid B is hardly observable in the others, and definitely not when terminal B is a slack bus, and so on. So this is the conclusion of that study, basically, that we use mode shapes of eigenvalues to identify the interaction between the generator located in the different synchronous grids. And we find that poorly damped electromechanical modes in one area are visible in the other AC areas through the DC grid. And they may be in opposite phase and sort of interact adversely with each other. But the source of that interaction is the shared control strategy using the DC droop. So the main conclusion is the level of interaction is mostly depending on the type of control and the way it's tuned. Then there is some other examples of analysis. What we want to do, there is a concern now that with more wind power and other generation that is interfaced through frequency converter, that you actually decouple the rotating masses of your generator from the electrical grid. So there is a reduction in the actual inertia of the AC grids, which is one source of more frequency variation. So there is a strong requirement being proposed that wind farms, for example, should provide this, what you call, what is referred to something as synthetic inertia, or that they contribute to fast response to frequency deviations. And then one could ask, when you design controllers to provide inertia response, will that also act to damp the electromechanical modes, or will they will it work to destabilize them? So that is the research question in this case. The same or a little bit simplified version is made here, and the point here is that the terminals here is equipped with frequency droop, but also with a phase compensation, so that they should act as with inertia support. So So essentially this is a proportional plus limited derivative controller. Inertia response, right, can be seen as more or less as derivative term. When you have a response, the rate of change of speed is somewhat governed by the inertia. So if we want to emulate inertia, we need to provide power that is proportional to rate of change of speed. And that can be done to proportional plus derivative controller. And these are tuned in a specific way to do that. It's tuned to help the governor, sort of damp the governor mode. So we have here a loss of load in grid number B, loss of load over here, that results in a rise of frequency. Okay? If you have a traditional control of the converter with no interaction with the frequency, okay, you don't get any response from the other side, so the frequency will rise and hopefully settle that. But you have a dramatic rise in frequency here. If you add on frequency droop, you get a certain response from the other side, which work exactly as the example I started with. But if you add some derivative term that we could call inertia support, you get the red response, which limits the rise of frequency even more, and you get more support from the other side. So this looks perfect in the way I see it. You help the other grid substantially with this, and it stabilizes and everything is fine. Now, if you look more closely at this, here you see the time range, 20, 40, 60, 80, 100 seconds. So this is the governor mode. If you look more closely at it, you can also look, you see that there's something happening on the electromechanical modes. And actually in this case, the solution with that had the inertia support result in a much reduced damping of the electromechanical modes. So even though it worked perfect on balancing, it destabilized the electromechanical modes. So the conclusion here is that you need to know what you're doing. You need to design the controller in a little bit more complicated way, so you don't destabilize one mode when you stabilize another. Then I think the final example I will do today is on frequency control support from offshore wind, which is of particular interest then in the North Sea, with the expectation of very high amounts of wind energy. And then I have advocated one solution today, that the support should be based on voltage droop and frequency droop compensation on the converter controls. That is possible, but you could always do it in another. You could also do it in another way. Depend on that you explicitly signal information about the frequency in the onshore grid through communication. One solution is based on that AC frequency change implicitly through the voltage droop of the DC grid. The other, that the onshore frequency is explicitly transmitted to the offshore wind farm through a communication network. That gives two different control implementation. One is based purely on the local measurement on voltage, DC voltage. The other one is based on the transmitted frequency, the transmitted measurement of frequency in the onshore grid. So a similar example again, two AC grids having different frequencies and the wind farm feeding in. This could be a wind farm, for example, feeding into England on one hand and Germany or the Netherlands on the other side through the network. Okay, and this is implemented in Power Factory, and in one case we use the local control scheme, and in the other case we use frequency in AC grid number 1 communicated to the wind farm. So the service of providing reserves is essentially going to be to this grid. They have they are communicating their frequency to this wind farm to provide reserves to this grid. And then, well, what happens to this? We don't know before we have analyzed it. And then there are several cases to be studied. When you do a local solution without communication, that's case 1, it's the red. Okay, it does provide something, and if you have direct communication, you can make it provide a little bit more reserves, but it's not a significant impact on this, but it is one contribution. And there is a side effect also, that the other system is influenced. But if you look at the numbers here, they are quite small, 50.01. So this is not really important. It looks worse than it is. This is the frequency deviation here is 10 times higher than here. Okay, so now the next example is what is the fault is on this side. Well, in one case where this is the frequency is communicated directly, of course, there's no change in frequency here because there is no voltage droop control on this one, so nothing happens. And that may be no signals, no support. Sure. And then the next one is when the fault is on this side, and they both have voltage droop, both the converters. Then you get similar result as in the first phase. It's okay. But the main difference is in this case where the loss of load is in this area, and they both are on voltage droop. Then you see that, okay, in the case where there is local control, so the voltage is used as the signal, you get a response, of course, because now it doesn't matter if the fault is here or here. This is sensed here anyway from the voltage, so it does respond. If you take frequency directly from this side, when the fault has happened here, there is an interaction, so it will be sensed, but it will not support very much. So this is a matter of sort of selectiveness. What do you want? I think that there is an advantage here with using the local signals, because you get support also to both areas, and you get no significant adverse effect with that. It may be a little bit different to follow the details here, but it's the kind of question you have to ask when you decide a controller that has system-wide implications. So I think it's time to wrap up. Yes, you're getting tired. So on this, what we showed here in this lecture was small signal analysis and simulation studies with 3 separate AC grid connected through a multi-terminal DC grid. And we used mode shape, an eigenvalue analysis to analyze interactions. And we saw that there was some level of interactions, very much due to control strategies. The main conclusion, however, that is the main message from this, is that is to say that it is possible to design control schemes that makes interconnected AC-DC grids behave almost like one AC grid. And that is why I advocate to look into solutions that instead of having huge AC interconnections, you could consider breaking AC interconnections up and having overlying DC grid. I think that in countries like India, I think that could be an interesting solution, because it behaves like one interconnected grid, but it's less vulnerable to a total blackout, I think. The stronger interactions, of course, you have to be careful about. You have to analyze it. But the stronger interaction makes it possible to supply reserves throughout the system and also add more sort of inertia. And we, at least in our analysis, we have found no evidence of serious adverse interaction as long as you have somewhat well-tuned controllers. So with this, I thank you for your attention, and if you have some questions, I'm still here. Yeah? Are you? Yeah.
How many terminals MTDC exist? So just like this case.
Yeah. How many multi-terminal DC systems there exist? That is not so many yet, but they are coming. The main obstacle for the time being is the challenges related to protection, because if you need DC breakers to protect a multi-terminal grid, that is still expensive stuff. But when that is solved, then there will be. There is one 3-terminal link in Sweden now. I think there are some on their way in China.
This is real case study.
This is my studies are only based on hypothetical grids, right? Yeah. So it's the principles that we have studied.
I have studied that master thesis.
Yeah, I remember. Yeah, yeah. I remember that. Now we're still on the research level, but this will come. I'm quite sure. Yeah. Oh yeah. It is. We have papers on that small signal, how to do, how to model the, how to set up the linearized equations. You mean, and do small signal analysis? Yes. Hmm? Yes. There are. I didn't mention any names here. I'll see what I have. No, there's no here. But my colleague at SEDE, she has, that's what she did on her master PhD, right? So that's why we had this analysis. Her name is SEDE. If you search for paper of her, then you'll find it. And I'm the co-author also, so that you search on me, you should find it, yes. Yeah. Tuning methods. Well, I prefer simple methods. That's my answer. But you can. I mean, I would.